for the DCB. That means this is the crack. Okay, so this is the DC specimen. So how the crack will form? Okay, that is where actually the G1. So the G1 is depending upon the parameters like crack length, A, H, thickness of the beam, material, Young's modulus, then this breadth B, height, then the applied load P. So based on that, the G1 we will get theoretically. Simultaneously, we will get through experimentally. Experimentally, you make the same specimen, you will get the same G. You may ask the question that how I can experimentally I can find the energy. Experimentally, I can find the energy. So people will not find the energy directly from the experiment, but instead of they can gain the stress and strain from the system. From that, they will calculate the G. The other way I can do through numerical analysis. FEM. Same model, you just make it in the any tool using by any tool. You can find the G1. Apply the load, you can. The thing is, this statement. Okay, the statement what it means, because somebody is making the specimen by having some kind of A, some kind of geometrical parameters. B may be constant, maybe a unit width or something like that. B is not a problem, but the H and the A, people may go with the different parameters. Means for the same material, for the same load, people may end up with different G's. It may not be correct. So to make the it is a standard testing procedure, no? So to make it to be consistent, if you make the, or if you have the H, which is equal to the A to the power 2 by 3, such a way that you are making means any value of P, or you will get the consistent G. If this parameter you make such a way that this will become a constant means, this becomes a constant means, okay, so your material is a constant, okay, your B is a unit thickness, this is a constant. If this parameter also constant, so every respect to P, you will get the constant value. You will get the constant value. Suppose increment of P, suppose one particular P, if I'm getting G1 is this much means, okay, somebody did the same somewhere with the same load, they should get the same G. If you maintain this particular parameter, H is equal to, okay, H to be made in terms of A to 2 by 3. This is the purpose. Then you can see here, basically the main important, this is the double cantilever beam. Basically, it's supposed to be like this. It's supposed to be like this, but because they made something like this, because why? Because the crack should really, okay, march towards the horizontal direction, okay, towards horizontal. Then only I can easily get the parameters. So how to make it means, so okay, you can see here the H, okay, the what you call that H, the H you can see here, the H, okay, whatever A you are providing, you have to make this H. So you have to, just a minute. Hello.
Good
Pardon?
Good afternoon, sir. This is Amog. Am I talking to Dr. Shiv Kumar?
Yeah, I'm in the class. Can you call after an hour? Okay. So you have to make, okay, the what you call that, the specimen, okay, the specimen H and A, the ratio, that means something like as long as the A grows like this, the H supposed to be like this. um, that means H is increased such that, okay, that means you have to increase the H. Okay, you have to increase the H. How, what, in what fashion? Okay, the A square by H cube should be a constant. Okay, that means what? Okay, H you provide A 2 by 3. If you make a specimen something similar to that, okay, then you will get the constant G in every test for every P. Okay, every P you will get a constant. Wherever you do, you will get the constant. For that purpose only, they made this change. Now, the crank has to go, it should not go like this. It should not go like this. It has to go a horizontal path. So for that, actually, they are making this groove. Once you have this groove, so crack exactly will pause on this particular thing. So I will get the consistent value of G for even the post-crack scenario. Post-crack scenario. This is very, very important. Crack, how the crack is marching and things. Okay, because the A keep on increasing, no? This is initial A. This is initial A. After that, what will happen? The A will increase, no? Every delta A. A will increase, no? So for that purpose only, we are making this H is it be A to the power 2 by 3 you make. So you will get the consistent G. You will get the consistent G. Okay, that is where we stop. Now, you can see one example, okay, to finding the energy release rate for the mode 3 scenario. This is again a DCB specimen only. DCB only. So, mode 2, okay, what is, this is mode 3. Mode 3 means what? Tiring mode. Okay, tiring mode, you know the tiring mode. It's something like, you know, this will come like this, one side. The another side will go like that. Okay, initially it was here. Now it got moved to this point. This is a tiring mode. So such a way that you apply moment, okay, the tiring will happen. The tiring will happen. So how to get the energy release rate? Energy release rate for cracked body subjected to a moment. Earlier we were applying force, DCB specimen. Now it is moment. It is become third mode. Once you apply moment, a tiring will happen, then it will be a third mode. If that is the case, so this is the energy. This is the energy. Okay, when a beam is being given moment, how much the energy? Okay, a beam. This is the energy for one single beam. Strain energy. When a beam, okay, is something like given a moment, something like this, how much energy means? Okay, 0 to L into the m square to m. This is the moment. Suppose a beam, suppose I am giving a moment here. This is L. So what the strain energy will develop means, okay, 0 to L m square by 2I dx. This is x. So y2 means here to top and bottom. So this is the total strain energy. Here, what is my L? Here the L is A. L is A. And dx will become dA. So I just simply look into this. Okay. 0 to A, m square by 2A. Instead of dx, I can go d. Just to substitute my moment of inertia, hbq by 12. Okay. I will get the total strain energy is 12 m square. M is the amount of moment you applied. A is the crack length. E is Young's modulus. H is the height of the beam. B is the width. Then you will get this much is the strain energy. But what is strain energy release rate or energy release rate? Okay, energy release rate is nothing but du by dA. This is what we got now in the previous slide. 12 m square A by EHBQ. So du by dA. So just you do that, this formula, it will become A will get cancelled. There is a 1B. So 12 m square EH B power 4. What is that? G3. G3 means what? Energy release rate when in the tearing mode. That is mode 3. This is one example to understand. Okay. Now, after all these things, because we are in the process of looking the in the energy release rate. Okay. Now, slowly we are entering into COD. I told you already. This is one of the fracture mechanics technique. I told you when energy techniques, stress technique, then J integral and CTOD or COD. This is crack tip opening displacement. This is crack opening displacement. This is crack tip opening displacement. That is here, CTOD. COD means this one, crack opening displacement, through which also people used to design or do the fracture mechanics calculations. Basically, this one I supposed to take after I introduce the stress techniques, but due to some reason, now I'm going to slightly introduce some of the terms in the stress techniques. Okay, the stress domain techniques, but very elaborately you will see these explanations in the stress techniques. But now only I just introduce simple terms here, then I will proceed with the theory right now. So I told you this is one of the design method. Okay, one of the design method, COD, because to calculate the COD is one of the fracture techniques, one of the fracture design technique, COD. For the mode 1, okay, for mode 1, so you may wonder, sir, most of the time we are seeing mode 1, and what about mode 2 and mode 3? We will see later. The majority of the, especially we are talking about energy release rate, and also moreover, this is mainly suitable for brittle type of materials. And also now slowly we have extended to M3, mode 3, and mode 2 also we will come. But very elaborately we will see in the stress techniques, that is stress intensity techniques, we will see the mode 2 and all very elaborately. Here we are mainly focusing on mode 1 type of failures. Okay, mode 1 type of failures, because it's more commonly encountering failures. Okay, usually the material encountering failure mode. Mode 2 is a sliding mode, you know very well. It's not much popular or common in reality. Okay. So let us actually spend some time on the crack opening displacement. That means I'm going to estimate, okay, when I apply the load, how much the crack will open, how much the crack will open. how much the crack will open. This one, this one, this is crack. This is the crack. So here you can see one term called Z1. Z1, this is capital Z. This is small z, okay? This is small z. Both have different meanings, okay? The author could have changed the notations, but somehow he is keeping the same thing. But okay, this is a terming function. This is location. Capital Z is a function. Small z is a location. Location. This is location, 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 location. Okay. So what is this particular Z1? I told you, no, this is a function. Stress into Z into root of, okay, Z square minus A square. A means what? This one. Z means at any point the location. So this is a function developed by Westergaard. This is a stress function basically. It is a stress function basically. It came from a stress function. You must have actually heard about Airy stress function. This is actually two-dimensional solution procedure. Two-dimensional solution procedure. Airy stress function. Because why it is related to here means because in any fracture mechanics, we are dealing with very thin structures. Thin structures. So thin structures means it is a two-dimensional member. It is a two-dimensional member. So here what is the interest? Sigma x, sigma y, and tau xy. Only three unknowns. Only three unknowns. So to find the three unknowns, Airy developed a concept to find the sigma x, sigma y, tau xy. It's a solution procedure by Airy. So for sigma x to be solved, Airy's function talks about in terms of pi. He will give solutions that we'll see later. So we need to have pi. What is this pi? Airy stress function. I hope I'm not confusing you because these terms I think already you might have experienced or you might have come across in your earlier studies. Even you did not actually, no problem. We will see it when we come to stress function. We will spend some time on Airy stress function. So this is basically came from Airy stress function. In that level, you can keep the knowledge right now. Hope, is it okay? Fine?
Yes, sir.
That girl?
Yes, sir.
Good. I could not recall your name, ma. That's what I'm calling girl. Sorry, okay. It's suddenly I cannot recall your name. What is your name?
Sandhita, sir.
Uh-uh?
Sandhita.
Yeah. It's difficult to keep that thing. Santita. Okay, I hope you don't mistake me, no? If I call you a girl. Fine. Okay, so this is a stress function, okay, Z. Then this is Z prime. Integral of this fellow is this fellow. Just, okay, integral of this fellow. Instead of the one integral on dz. It's a z prime. This one is you guys very well that when there is a suffix 1 means it is pertinent to mode 1. Okay, in the similar procedure, in the Westergaard solution procedure, they have given the solution for uy. What is uy? Uy is the displacement. What is uy? Uy is the displacement. This is basically x-axis. This is y-axis. So this is okay. Uy means displacement in y. At any point you can take. Here uy, okay, 0, something like that. Uy. Uy, once you solve this, you will get the uy. To solve this one, what do you need? I want imaginary part of this fellow. I want real part of this fellow. These are all highly mathematics. That's what I told. When you're really getting into fracture mechanics, slightly it will end up with the mathematical terms into that. But we are not doing very rigorous mathematics. Only thing we will get the flower of mathematics, flower of how it sits. That's all. We don't really getting into more mathematics into that. But ultimately, we have to understand that we are all very familiar with logarithmic or integration or differentiation or matrices. These things we are all very familiar, isn't it? Now some kind of algebraic equations. These are all commonly we are exposure. When I go very deep mathematics, asymptotes or partial differential equation or differential equation solution, that may need some kind of boundary solution. So many things there. But these things, preliminary things I need. This is sufficient. So we will work within that level only. We do not go to very deeply to solve some kind of simultaneous equation by putting so many hardcore things. Not like that. Okay, so don't be afraid. So let us coming to this theorem. They have given solution for uy. Once you solve this, you will get uy. Okay. So this you need not really bother it right now. That we'll see later. Okay. This I will come to later. Now, our focus is what? Our focus, we need to find uy. Why? We are now in the area of to find the crack opening displacement, COD. So I want to estimate for the given amount of load, how much my displacement. And that is my focus right now. So for that particular aim, what are all the things I need? I need to estimate my uy. My uy. So how to get my uy? Once I solve this equation, I will get. To solve this equation, what are the things I need? I need this and this. What is this? This is the stress function. This is integral of stress function. This detail you will come to little later. Okay. So now we are marching that. So I need to do. So now I'm going to do the process of this. Next slide. What is that? I need to get the integral of that. For that only I am doing now. You see here, z del z by z square by a square. Same thing. That integral part I am taken. To make the integration easy, I can take this z square minus a square as m. Okay, m is function of again z. So if I partially differentiate I on this side, this constant will go off. So dm into 2z dz. Keep it your side. Keep it this aside. I want to know integral of that. So Balaji, I'm in the class. Anything urgent, Balaji?
ஓகே இல்ல இல்ல நாளைக்கு ஃபர்ஸ்ட் 2 hours எடுக்கலாமான்னு கேட்டேங்க. ஏன்னா அது முக்கியமான கிளாஸ்.
இல்ல, you have to be in the interview, Balaji.
அப்போ அந்த கிளாஸ் கேன்சல் பண்ணிடலாங்களா ரெண்டும்?
ஆமா.
ஓகே ஓகே ஓகே.
Yeah, sure. Yes, tomorrow is working day, pa, for us? Yeah, of course, it's working day. Hello?
Sir?
Yeah, tomorrow working day, I believe.
Yes, sir. Tomorrow is working.
Okay. You guys know that we have started a new MTech program?
No, sir.
No?
No, sir. No, sir.
No, sir. Actually, no, sir.
Sure, no. I see. You know that we have accredited with the A++ NAC?
Yes, sir. Yes, sir.
Yes, sir. Yes.
Good. Okay. So in the same time, we got last month or a couple of weeks back. Okay, we have got actually. We have got. I should not say we have got. In fact, actually, this was the initiation by the AICTE and DRDO. So they have actually, this was the, what you call that, incubation of these two companies in the sense forums. Now, the currently India, this last 1 decade, we are, indigenously we are developing a lot of, defense things, no? Aircraft, blah, blah, this, that, and so many things we are doing, no? So by keeping in mind what they found that, something like they need more engineers in India to meet the current, what you call that, emergency or, current development. They need more engineers. So they thought of, they requested in India colleges like us or the grade 1 colleges, why don't you start MTech in defense technology? MTech in defense technology, under which there are 6 streams they came. The one stream is aerospace technology. Another space is communication, high energy materials. Then so many 6 divisions actually, specialization they have offered. So colleges would like to, they have given some conditions. The college should be within this particular rank, NAC accreditation, so many criteria. If you have, you are eligible to start this particular thing. So suddenly it came. So we applied and we got the permission for aerospace technology, that is defense technology. So, 2 specialization we got. One is aerospace specialization, another one is communication specialization. So these communications will be dealt by EC department of our Coimbatore campus. This will be by our own aerospace. But as an overall, the whole proprietary comes under aerospace. So that means this is our course. EC is taking classes for us. That is their specialization. But this comes under our aerospace umbrella. That means from this year onwards, actually, we are going to start MTech in defense technology. Already we have made the publicity, and we got strength 30. Now we got 27 applications. Okay, so tomorrow is the interview for that. So what exactly this means? The aerospace, highly the subjects, this is a 2-year term. The first year you will have 2 semesters, second year you will have 2 semesters. So these 2 semesters completely project. So what is the specialty of this particular model? The project you can do it at the any DRDO lab or ISRO, not only limited to anywhere you can do your final year project. All the subjects in the first semester, second semester, you will have 6 subjects, 4 core and 2 electives. Majority of them are related to the defense thing. So in addition to our faculty members, we will actually, hire or we will get the contract from the, ex DRDO scientists. No, they will offer the courses. Some of the courses they will come here and offer, or sometimes they will offer through online. Because of the pandemic, things may be online. Maybe once the situation normalized, they will come to our campus and stay with us for a semester, or some kind of fast track mode we will do. Within 3 weeks, we will complete that particular thing. Like that, we don't know the modality exactly what we are planned, but this is how we will manage the things. We have 2 labs here also. Here 2 labs, here 2 labs, first semester, second semester. Again, those labs will be taken care by the DRDO labs. So a particular lab will take the students to the particular center. We don't know which lab in India we will choose. That process is going under. So people will do their laboratory also there, and end project also any of the DRDO labs. But what is the advantage of this thing is definitely it will give you very good insight about the defense technology, and also a very potential candidate for the meeting the current requirement. The only thing is the job you can get any DRDO laboratories, but there is no guaranteed a job right now. But we have actually planning, because already AICT DRDO, they only incubated this idea, no? So definitely we will get a lot of things. And not only we have to look for only the government laboratories, but a lot of private firms also have started a lot of defense technology, L&T, Waltz and Tata, Godrej, almost all, okay. BrahMos, so many companies are there actually. So this will be an added advantage to get into that particular companies when you are really looking for core companies. Okay, when you're really looking for core companies. And maybe in future we will push, because now how DRDO recruiting scientists means they are going to IITs for the direct recruitment. So slowly we will pitch, maybe down the line we will pitch to DRDO that let you please come to Amrita for the recruitment for this particular, because a BTech level they don't come, but MTech means definitely we can request them to come for campus placement or recruitment. So in that sense, we may push somebody through that particular placement procedure also. So this is the outset of the defense program, what we have currently have. Any doubt, Ma, in this process?
Sir, is application based on gate?
Yeah, that depends actually. Now we have a 20. Now we are looking for the gate, non-gate, everything, but we will give first preference to gate.
Okay, sir.
Gate, then our own students.
Okay, sir.
Sir, you said we got this aerospace technology division, sir.
Specialization.
Sir, then basically we'll be learning about more military side of everything, sir. Then.
Yes, ma. Actually, some of the subjects, military, avionics, combustion with respect to rocket system, then equipments, then missile systems, designing, the 50 to 40% mainly on the electronic side, ma. Avionics kind of things. 50-50, I would say. Structures 50 on that 50. Again, you can choose the specialization. You can choose the electives. Suppose you want to get into more electronics also, you can get into that. You want to coming into more on structures, you can come. Okay, you have the flexibility in the semester 1 and 2.
Okay, sir.
It's a good model actually. Good. This is a very unique one actually, this particular program. You can think of once you complete. Okay.
Yes, sir.
Sure, sir.
Yeah.
Yes, sir.
Yeah. Fine. Okay. We will come to our model. So to make the integration, we just a simplification made, and that is integrated. Okay, into this is the thing. So sigma into 2. So this 2 and 2 get cancelled. So sigma into root m. What this solution? Okay, this solution. Let us go to the next slide. Okay, this is what all it is. Okay, this gets cancelled. So I will get sigma root m. Okay, so again I'm resubstituting my z square a because I know that no m is equal to square. So sigma into x square by. Okay, so now here y. So our main location is this is the crack, no? Okay, so this is x-axis. This is y-axis, isn't it? No. So I'm looking for the maximum, this point. Okay, this point. So this point y equal to 0. So my location z in terms of x. Okay, so when I say y equal to 0, I can make my z as x because it's a variation. I'm looking only in this direction only. My z, I'm looking for the solution on z. Then only I can trace my y. Okay, so z will become x square. Now I'm taking this particular negative outside, so automatically the imaginary part will come. Okay, imaginary will come. So in this particular thing is imaginary of sigma into a square minus x square. I hope this part is clear for you. Now what is our aim? To find the uy. So to find uy, I need imaginary part, real part. Now I can substitute. So y equal to 0 because I'm looking in this direction from this point to this direction. So y always 0. That is, this will cancel. So imaginary part of z part only in the previous slide we have got. I means imaginary part of z prime. Okay, so 2 by 1 plus mu z into sigma a square by d square. Okay, so once I rearrange the things, okay, it will become like this. So this and this get cancelled, something like that. Now I got my uy. Okay, uy I got it 1 by g into sigma by 1 plus this. Right now, okay, now uy is 2z. Okay, 2 sigma. That means okay. So now COD. What is COD? COD means here one more uy is there. Then only I can get complete. So that is what 2 times my uy. That is crack opening displacement because I want to see complete crack to be opened. So 2 I had to multiply here. So this 2 do get cancelled. That 2 will be there. Okay, this is what it is. Now, so this and 2, okay, 4 sigma. Okay, this I can simply arrange, no? You have the relation, no? E equal to 2g into 1 plus. This is the elastic constant relation. I'm just replacing g in terms of E. That's all I have done. Okay, into a square minus x square. So my COD, crack opening displacement, is 4 sigma by E into root of a square minus x square. X square means, okay, it will go like this, x square. It go from 0 to wherever thing, a, something like that. This is a. So what will happen if x equal to 0? What will x equal to 0? What I will get? I will get the maximum, isn't it? No, 4 sigma E by a. If I want to do it here means 0 because what the displacement is 0. Y is 0. You can see here. This becomes a. Everything will go to 0. So this is what, okay, COD. This is what COD, crack opening displacement. What is this use? Because the crack opening displacement is one of the criteria I supposed to find. The crack opening displacement is one of the criteria in the design process, because I can make sure that my COD should not exceed like this. I can set a criteria, or I know my materials ultimate capacity, application of load level. I can know how much deflection I know which deflection or which opening a crack will become developed. So I can control, or I can check that particular values with this particular value for the design process. How you say G should be less than G1C or K should be less than K1C, like that my COD should be less than my materials strength of the thing. So for that purpose, this has been useful. So when my COD will become more, if I increase my sigma, obviously opening will more. If I increase my crack length, obviously my open will more. If I increase material strength, it will become less. So this is the formula. The maximum COD at the tip I can get 4 sigma A by E. Is there any doubt? We will stop the class at the moment here. Any doubt now?
No, sir.
No, sir.
Okay, so can we wind up the class now?
So,
Yes, sir.
Yes. Okay.
Yes, sir.
Yeah. Bye.
Bye.
thank you.
Bye.